All right, let's dive right into a really cool topic in organic chemistry. One that seems simple at first glance, but actually hides this fascinating paradox, the basicity of amines. It's a perfect case study of how a nice, neat theory can get a lot more complicated and interesting when you test it out in the real world. So let's get straight to the puzzle.
So here it is, the big question that trips up so many people. We have a solid chemical principle, right? It makes a very clear prediction. But then, we go into the lab, we run the experiment, and the results, well, they often come out completely different. Sometimes they're even backward. So what on earth is going on here?
And this slide just lays out the conflict perfectly. On the left, that's what we expect to happen. Based on something called the inductive effect, you'd think the more alkyl groups you pile onto an amine, the more basic it gets. So tertiary should be the strongest base, no question. But then, you look at the reality on the right. In water, the whole thing gets scrambled. Secondary amines are often on top, and look at that, tertiary amines can sometimes be at the very bottom. This isn't just a tiny rounding error, it's a huge contradiction we need to figure out.
Okay, so the key to cracking this puzzle is realizing that basicity in water isn't a one-man show. It's actually a three-way tug of war. We've got three different chemical effects all battling it out, each one trying to pull the final result in its own direction.
First up in the ring is the inductive effect. Now, this is the one that gave us that first simple prediction. And the logic on its own is perfectly sound. Alkyl groups are electron donating, meaning they push electron density toward that central nitrogen atom. The more alkyl groups you have, the more electron-rich that nitrogen gets, and the more it wants to grab a proton. So if this were the only thing that mattered, tertiary amines would win, hands down.
But here comes our second contender, and it's a big one, the solvation effect. See, a stronger base is one that forms a more stable product after it accepts a proton. And in water, that stability comes from hydrogen bonding. Here's the kicker. The more hydrogens you have on that nitrogen, the more hydrogen bonds you can form with the water all around you. This means the primary amines conjugate acid gets the most stabilization from solvation, which completely flips the order of who's favored. And our third factor is what we call steric hindrance. You can just think of this as a crowding problem. Those same alkyl groups that were helping with the inductive effect, well, they're kind of bulky. They physically get in the way and block water molecules from getting close enough to form all those nice, stabilizing hydrogen bonds. This problem is worst for the super-crowded tertiary amine and barely an issue for the primary amine. So this factor also favors the primary amine being strongest.
So let's recap the fight. We've got the inductive effect screaming for tertiary amines to be number one. But then you have both solvation and steric hindrance teaming up and pushing for primary amines to win. So, how does this all play out? Who actually comes out on top?
And the winner is, drumroll please, most of the time it's the one right in the middle. The real-world data consistently shows that secondary amines are almost always the most basic in water. They've found the perfect sweet spot in this chemical tug-of-war. So, why is that? What's their secret? Well, let's break it down. On one hand, secondary amines have two alkyl groups, which gives them a way stronger inductive effect than a primary amine, so that's a big plus. But on the other hand, their conjugate acid still has two hydrogens left on the nitrogen. That allows for really good stabilization from solvation, way better than what a tertiary amine gets. It's this amazing balance, the best possible compromise between all those competing forces.
Now it gets even more interesting, because this battle doesn't always have the exact same outcome. The results can actually change depending on just how bulky those alkyl groups are. So let's look at two classic examples to see how the balance of power can shift.
Okay, first up, methylamines. With these, the observed order is secondary, then primary, and dead last is tertiary. Why? It all comes down to the fact that methyl groups are tiny. They don't cause much crowding at all. This lets the solvation effect become the dominant player. The amazing stabilization that the primary amine gets from water is so powerful that it completely outweighs the stronger inductive effect of the tertiary amine. Solvation wins this round.
But now watch what happens when we swap those tiny methyl groups for bulkier ethyl groups. Look at that, the order changes. Secondary is still our champion, but now tertiary actually beats primary. Those bigger ethyl groups do two things. They beef up the inductive effect, and they also create more steric hindrance, which weakens the power of solvation for everybody. In this new fight, the stronger inductive effect of the tertiary amine is finally enough to push it past the now poorly solvated primary amine. The balance of power has shifted.
So,
Let's bring this all home and just summarize the trade-offs that each of these amines is dealing with in this constant chemical battle.
And really, that's the main takeaway here. There is no single best feature. To be the strongest base, it's not about being the best at one thing. It's about balancing all of the competing strengths and weaknesses. It's a constant battle of trade-offs.
This table just lays it all out so clearly. You've got the primary amine over on one side. It has a weak inductive effect, but it wins big on solvation and has almost no steric hindrance. Then, way on the other end, you have the tertiary amine. It's the king of the inductive effect, but it pays a huge price with terrible solvation and lots of hindrance. And right there in the middle, you have the secondary amine, a good inductive effect, good solvation, and just moderate hindrance. It's the all-around athlete. It might not be a specialist in any single category, but it's the one that wins the whole competition.
This just goes to show you, sometimes the most interesting science is hiding right where our simple predictions break down. It forces us to dig deeper and uncover a much richer, more complete story. It really makes you wonder, doesn't it? What other simple rules that we learn in science are also hiding a much more complex and fascinating reality?